Okay, here's a problem with potential difference circuits. We're asked to find these three values. We know some values of potential difference in the circuit, and let's move ahead. First, I want to understand what happens in this circuit. Well, I've got some positive terminal to the battery, the cell, and I've got a negative terminal. We always assume that what moves through the circuit are a bunch of positive charges, like this. So the positive charges are all being urged out from the positive terminal, right? They're moving to the right, flowing out of the positive terminal. After all, batteries are devices that separate all the positives on one side and the negatives on the other. So when you finally connect a wire, what we pretend in physics is that the positive charges can move. So they flow out and they're repelled from the other positives in the terminal. We pretend that the negative charges, we pretend they're fixed. We act like they are immovable. They cannot, relocate. So naturally, in a battery, charge flows from positive. It goes around, and those positive charge carriers, they flow toward the negative terminal because positive charges are attracted toward the negative terminal. And when that happens, when we have charge flowing like this through a battery, the battery gives energy to the charges. That's why this is going to be a positive potential difference. All right, so charges flow out, they move to the left. Get rid of all this. And what I'm going to do is draw a loop that goes, it's going to start here. We just went through the battery the way we're supposed to, so that's positive 9 volts. We're going through this resistor. Resistors dissipate potential difference. We're traveling the right way through the resistor. The charges, maybe they go up and they go through the 2 volt, the next resistor. We're moving the correct way through that resistor. So again, we lose energy, we lose potential difference. Then perhaps we go down, we go through the 1 volt, and this is another spot where charges are losing potential difference, losing energy. And we continue through the circuit, and then we get to V3 where they lose their final amount of energy. Oops. That's a negative value because they're losing energy across that third final potential resistor. Fourth resistor, I guess. So we solve for V3, right? This is in volts here. If you do 9 minus 3 minus 2 minus 1, that's going to be 6, is what we subtract, and you get 3 volts equals V3, like that. Okay, 3 volts. Now, how did I know which circuit, which loop to start with, right? How did I know which way to go? Well, every time there was a fork, I took the fork with the known potential difference. Pretend for a second you went through this loop. Well, now there would be 1, 2 potential differences we do not know, and if you have 2 unknowns in the equation, you cannot solve that equation. That's how I knew that I should be going, I'm thinking, okay, let me go through. There's a junction. Well, I know that potential difference, and I don't know this one yet. So let me go the route where I have something that's given. And then I get to another junction, and I say, well, I know that potential difference. V2, I don't know. Let me take the route that's with the value that's given. And then we're forced through V3. Okay. Next, we find V2. Oh, this is easy. Parallel resistors always have the same potential difference. So that's going to be 1 volt. We could also use the loop rule. We gain 9, we lose 3, so now we're at 6 total. Left, 6 remaining. We lose 2, so now we're down to 4. We go this way, and we're at 4. V3, that's going to be 3 volts. So if we had 4 up above earlier, and 3 is lost later, V2 would have to be 1 volt. Finally, we look for V1. So I'm going to follow a loop that goes through V1. I'll start here. I gain 9 volts. I lose 3 volts. I lose V1. I lose V3, which is 3 volts. And let me write it out. I'm gaining 9 at the very beginning. I lose 3 at this resistor. I lose some at V1 across that resistor. And then I lose some at V3, which is 3. And when I solve for V1, that's going to be 3 volts as well. Well, this all came out pretty simplistic. That's okay. All right, next up. V2, V3, find all these things. All right, 27 volts is the EMF of the battery. That's the total energy that the battery gives per coulomb of charge flowing through the circuit. And let's look and see what we've got here. Well, what do I know? I know the potential difference across this first branch is 12 volts. But wait a second, I have a rule for parallel resistors. They always dissipate the same potential difference. So V2 is going to have to be 12 as well. Then I can use the loop rule. I'll start here. I gain 27 volts. I'll take the top route. I lose 12, and I lose some last final amount before I get back to where I started. So I'm gaining 27. I am losing 12. I'm gaining some over R3. That all equals 0. And if you solve for V3, what do we get? Let's see. V3 should be negative. That's what I missed. Because we're losing potential difference across V3. So I'm going to add V3 to both sides, and this is 15. Okay. What's next? Well, let's look for the current. Move this all out. I1 and I2 and I3. Well, I1, the current traveling through the first resistor, and I2. We know R2 is given at 6 ohms. And we know V3, 3 ohms. So if we have V and R, we can calculate current, I2. We do V equals IR. We're going to apply this equation to the second resistor, R2. And when we plug in the potential difference value is 12, this says, equals I times the resistance is 6 we are given in the photo. And I2 comes to 3 amps. 2 amps. That's I2. All right, same thing for I3. We have V equals IR. That equation is always valid. For ohmic resistor, well, really it's always valid. And we plug in the value of V3. That's going to be 15 volts. We plug in R3, which is 3 ohms. That was a typo up there. We isolate I3, we divide both sides by 3, we get 5 amps. So how do we find I1? I1. We're actually going to use the junction rule. And that's going to make things really quite simple. Okay, take a look at this junction. The current going through I3, current here, passing through I3, all goes through the battery, the cell, it all bends down, and it all is located right here, entering this junction. So I'll call that I3, because that's the value of current through the third resistor. Up here, some of the current I3 splits up and travels along the top path. I'll call that I1. The rest of the current travels down along the bottom path, which I'll call I2. So we see that the total current going into the junction I3, well, I3 splits up. Some of it goes the top path and the rest goes the bottom. But that value, the amount going in, the current going in to the junction, has to equal the current coming out of the junction because there's nowhere else for charges to go. So I3 then is 5. I1 is our unknown. We plug in I2 of 2 amps. And what do we get? I1 comes to 3. Okay, on to the last one. First, I'm going to label the positive terminals of the batteries. I'm going to remember that positive charge wants to flow out of positive terminals, and the positive current wants to flow into the negative terminal. That's how normal batteries operate. So I'll be on the lookout for batteries that are backwards. We have to label some current. Here I'll call this first current I1. Right down here, the current splits into I2 and I3. So I1 is splitting up. Some follows the top path. Some follows the bottom. Okay, let's make a loop that goes, make a full loop. I'll start right here, and hey, I just went through the battery. I just gained energy because I'm going the right way. My positive 25 volts there. We're going into the negative and out of the positive. We keep following the loop around, and I just went through a resistor. So I lost potential difference, but V equals I times R. And the current we're dealing with is I1. We go through this 3 ohm resistor. We lose again potential difference. Resistors dissipate potential difference. And V equals I times R. We're still dealing with I1. I'll take the bottom path where I3 travels. That I3 those charges lose more energy across the 4 ohm resistor. So we subtract IR to show how much energy they lose per coulomb. It's I3 at this point, the resistance is 4. Then we go through this battery. We're flowing toward negative. That's where positive charges want to go. We're going out of positive. That's exactly the right way for this to go. That's a normal battery. We're gaining 10 volts. Normal batteries give energy to the circuit, to the charges. Then we lose energy in that 3 ohm resistor. How much do we lose? V equals IR, so we do I, which at this point is I1 again, times R. How do I know it's I1? Well, because the current here keeps going, and bam, it becomes I1. If we combine like terms, you've got 25 and 10, that's 35. Oh, whoops. All of this equals 0, by the way, because I made a complete loop. If we take the I1s, you've got 2, that makes 5, another 3 makes 8. Put them on the right side, they become positive. Put the 4 I3s on the right side, they become positive. Then we're going to follow another path. Start here. I go through the battery. We gain 25 volts. That's positive 25. We lose energy here. The potential difference we lose is IR. We lose energy through the next resistor, which is again equal to IR. We lose energy through both of those guys. This time we're dealing with I2, the current through the top branch. IR for both of those. We're flowing through a battery. We're flowing toward positive. Positive charges do not want to flow toward a positive terminal. That battery is backwards. That makes it negative. Then we go through this good old battery, the one connected the right way. And finally, we lose energy in the 3 ohm resistor, minus I1 times 3. That is all equal to 0 because we made it back around the entire loop. And we do the same thing as before. We combine like terms and write an equation. And at this point, what we have are 3 equations and 3 unknowns. We can use substitution to solve. We can set up some matrices. We can solve this using any of the algebraic techniques that we've learned. And we proceed to find I1, which is what the question originally asked for, the total current. work it out or do it in our calculator with a matrix, we get 3.3 amps.